Okay, everyone, welcome back to the lesson. We're still looking at the section on translating word problems into functional equations. In other words, taking a description of some phenomena, something that's happening, and writing it as a function. So I'm going to look at a couple of more examples on page 43, and we'll see how these work, how these come along. Now, remember, it's very important to be able to understand what it is you're being asked for before you even attempt to do anything with the problem. So let's look at question number 2 now on page 43. This says, express the area. And right away, just those first three words, they tell me that when I am finished this question, it better be A equals, A for area. Express the area. All right. Of a triangle. Okay, so I need the formula for the area of a triangle here. That's what we call the primary equation. Now, we're probably going to have to change some things in that equation depending on what else they're asking us for in this problem. So express the area of a triangle in terms of its base. Now, we can use B for the base. That means the length of the base. And that means that when you're finished with this problem, the very last thing you should be ending up with, yes, you're going to have area equals, but the only variable that should be on the right-hand side is B for the base of the triangle, the length of the base. Now, you're going to have other things there. You will probably have numbers and other mathematical symbols. Don't be surprised on that. But the only variable there should be B. Okay? So we need to express the area of a triangle. That's where the A comes from. In terms of its base, that's where the B comes from. Now, there's something else they're telling us, and I think this is going to be our secondary equation here. If the height is double the base. Now, that means something. We can get an equation just from that. But my first goal, the first thing I'm going to do is write down the formula for the area of a triangle. And I'm hoping you all remember that. It would be on that sheet anyway, the formulas. The area of a triangle is 1/2 the base times the height. Now, there's other formulas for the area of a triangle, but that's the one they're referring to in this case. Now, remember what you want, what you have to end up with. The B right there is absolutely fine. I can leave that B there because we have to express the area in terms of its base or as a function of its base. That's another way to think of it. But the H, that's got to go. That has got to go somehow. So you need to come up somehow with some kind of another equation that relates H and B. And I'm thinking, everybody, that this last part of the statement, the height is double the base, that's your key right there. The height, think of that as H, is, there's your equal sign, double means you multiply by 2, double the base would be 2b. Now, there's your secondary equation. And you don't want to solve that for b. You don't get the b by itself because remember, it's the h in that main equation that you're replacing. And this formula here is in the perfect form for that. So wherever I see h, I can replace it with 2b. And by golly, that's exactly what I'm going to do right here. So let me just come up into my next step. So the area of the triangle is equal to 1/2 times the base. I didn't change either one of those two things. But in place of the height, I now write 2 times b. And that's what I get from this secondary equation. Okay. Now, look at what you have. That basically is your answer. That is your function. I guarantee you that function expresses the area of a triangle in terms of its base. But we can simplify that a little bit. Remember that any constants should be brought out in front. So that would be your 1/2 multiplied by the 2. Well, wait a minute. Well, that's just 1, isn't it? That's just a 1. And you also have a b multiplied by another b. And that is b squared. So 1b squared or just b squared, that would be your answer, your final answer, nice and simplified for question number 2. Kind of simple, isn't it? Yeah, that equation actually looks pretty straightforward. It actually looks pretty simple. Okay, let's go to number 3. Let's try question number 3 here now. And again, we'll read it carefully. We'll read it very carefully. Make sure we understand exactly what they're asking for. Now, this one I see has 3 parts. Okay, so we'll answer all 3 parts. And come up with the correct answers for all of them. It says the radius of a balloon. Now, a balloon, remember, is a ball, isn't it? Shaped like a ball. It's actually a sphere. That's the mathematical term for it. And the only real measurement of a sphere that you need to calculate its volume or its surface area is the radius of the sphere. But it says the radius of a balloon increases from 6 centimeters. So that's the initial, I'll even write that word here, look. That's the initial size of the balloon. Think of that as time equals 0. Okay, t equals 0. But then it also says that it increases, which means it's getting bigger, at a rate of 3 centimeters for every second. Now let me say, let's introduce a variable for time here because it talks about seconds. So I'm going to let t equal the time in seconds. All right, you could use any variable really if you want, but I'm going to use t. That's one that most people use for time anyway. So let's see what we have. Part A, all that's asking for is express the radius, so r, as a function of time. So that means that when you're finished, the only variable on the right-hand side should be t. Well, actually, it's pretty straightforward. It has an initial radius of 6. So think of that as the very beginning radius. That's what it starts with, 6. Now, for every second that goes by after that, the radius has 3 centimeters added onto it. Well, that would mean it's increasing by, so it's plus. And if it's 3 centimeters per second, that's a multiplication. So it would be 3 multiplied by t, where t, of course, is the time in seconds. Now, think about that carefully. Make sure that this makes sense for the context of the problem. When t is equal to 0, remember that's the initial situation, the initial condition. If you did put in a 3 or a 0 for t, you'd end up with 6 plus 3 times 0. And yes, that would give you 6. The initial radius of that balloon would be 6 centimeters. As every second goes by, after 1 second, if you plug in a 1 for t, then you have 6 plus 3 times 1, and that gives you 9 centimeters after 1 second, which again, in the context of this problem, according to what we were told, makes perfectly good sense. So this is the answer for part A. There's no need to go any further with this. In fact, you really can't go any further with this than part A. I've expressed the radius, right, r, that's on the left-hand side, as a function of time. The only variable on the right-hand side is t. So we've answered part A. Now, let's look at part B. What does that say? Express the volume of the sphere. Now, you probably don't know that formula. You might. And if you do, great. But the formula for the volume of the sphere, everyone, is 4/3, 4 over 3, times pi, times the radius cubed. Okay, that's the formula for the volume of a sphere. That would be provided to you. And in fact, that's on that sheet I was mentioning to you as well. So, express the volume. So I've got my V equals as a function of time. Oh, look at that. They actually gave you the formula there for the volume of a sphere. Good for them. Now, that means that this R right there, that has to come out. That has to be removed from our equation. And in its place, we need to put something that's got t in it as a function of time. You need an equation that relates R and T. Oh, wait a minute. You just did that in part A. You see that? There is your secondary equation. That is actually what you're going to put into the main equation to end up with the answer to part B, express the volume as a function of time. So, and it's actually very simple. It's just an immediate substitution, 4/3 times pi. And now in place of r, I'll just put a big set of brackets there, all right, something cubed. And in place of r, I write something equal to r. So how about 6 plus 3t, like so. Now, that answers part B. And there's no need to simplify that, by the way. I'm not expecting anyone to cube a binomial. There's a fair amount of work to that. And I mean, that form of the answer looks pretty good anyway. There's nothing wrong with that. So we've expressed the volume as a function of time. Part B is done. Now there's one other part, part C. What will be the volume, or what is the volume of the balloon at t equals 11 seconds? So you need a formula for volume, which I think we got in part B, and we're given the time that has passed by. So that, everybody, means that we really just use the equation that we got from part B. That will answer part C easily, and all we do is plug in 11 for t. So V is equal to, if you wanted to, you could even write V of 11. All right, what is the volume when t equals 11? But you don't have to do that here, but you can. 4/3 multiplied by pi, and then in brackets, 6 plus 3 times 11. Now I'm going to put another set of brackets there for the 11, okay? So there's your implied multiplication. Now, of course, you multiply 3 times 11 first. Don't forget your cube. Multiply 3 times 11 first, and then add your 6 to that. You follow the order of operations. Now, everyone, you can just type that into your calculators directly. As long as you type it in carefully, 4 divided by 3 times pi times, and then a set of brackets, 6 plus 3 multiplied by 11, closing bracket, to the power of 3. And I've got the answer here. Now, you can just type that into your calculator. The approximate answer is kind of big. It's about 248,474.8. Now, your science teachers would be really mad at me seeing me write that down, because that's way too precise of an answer. That's way too precise. But in math, usually we say you can round it to 1 decimal place, which would be that. If you did decide to round that a little further, don't round it too much though. But the only number that we have here is 11 seconds, and technically that's 2 significant digits. So if you were really strict about this, your science teachers would be, then technically I could have written 250,000 cubic centimeters. Excuse me, that would be 2 significant digits. But I'm going to be a little more lenient than that in your math. As long as you round your answer to a precision where I can tell you got the correct answer, that's all I'm going to be concerned about. Okay. Now, that is the 3 examples on page 46. Beginning on page, page 43. Beginning on page 44, there's your practice problems. Now, number 1 is basically exactly the same type of problem you had in Math 1700. Can you take that expression and just write a very simple, is not usually even an equation for it, just write an expression for that. So if you have a number, think of the number as x. You can always use x for the number. Double it and add 7 would just be something like 2x plus 7. Anyway, you try the others. I've only got about 30 seconds left. Then I'd like you to try numbers 2 right to the very end. So that's on page 44, 45, and 46. Now, we're definitely going to be going over a lot of these in class, but you try them first. And so anyway, like I say, we'll do those in class. And that's the end of topic number 2, unit number 2. So I'll finish this lesson here, and I'll see you all in class. Bye-bye.